Hello there, Mr. Sutton here, bringing you this lesson on function families. In this one, we are going to classify and distinguish between different types of functions based on their graphs and their algebraic representations. And we will also be determining if a function is even, odd, or neither.
Okay, so linear functions. Hopefully you know what these look like, but if not, here we are. A linear function looks like a straight line, no curves at all on this. The parent graph is just y equals x. And by the way, by parent graph, we mean the most simple version of the graph that we can kind of base all our other graphs of this on. So some examples, algebraic, we've got y equals 3x. You can put a number out here. You can put an y-intercept, and we can make this negative. So here are just some different examples. The domain of a linear function is all the real numbers, and the range is also all the real numbers. Domain, remember, is all the x values that the function can take. You can plug any x value you want into this, and it's okay. The range is all the y values you could possibly get back. Lines give you back all the y values. This is, of course, assuming that you have a slanted line and not a horizontal line. Horizontal line, the range is just limited to that one y value. We're going to go through the rest of the functions in your chart now. So if you wanted to try the rest of those on your own, pause the video and take care of that. Otherwise, here we go. Quadratic function, that is your parabola that you may have seen before. Parent function for that, in the description here, that's just a U shape. The parent function, that is y equals x squared. Doesn't get any simpler than that. We can change this by putting things in front of the x squared, by putting things inside the squared part of this. This will shift our graph in various directions. For the domain, all the x values, you'll notice that this goes forever to the left and the right. You can plug anything you want into x squared and it'll give you back a real number. So domain is all reals, just like the linears. The range, you'll notice we're a little bit more limited than the lines. The lines were able to go down forever. This quadratic only goes one direction forever. So for just going based off the parent function for the range, notice that we can only get 0 and higher. So y greater than or equal to 0 for that. For the cubic functions, if you graph them out, that's the one with the x cubed. They look like this, kind of a weird S shape, snake shape. So these are cubic because you've got a third power there, third dimension, cube, if you want to associate those. And just like before, we can put things out in front of the x cubed. We can put things inside the cubed part. The domain for these is still all the real numbers. There's nothing that can't be cubed. The range, now we are back to all real numbers for this as well. Unlike the parabola, the quadratic, this can go both directions forever. And just another quick note while we're here, all odd functions that are third power or higher have this basic kind of shape, and all the even power functions like x to the fourth and x to the sixth, they all look like the parabola we saw on the last page. So with these polynomials, you really only have two choices, snake and u. The only other choice is a line, which is just a snake without a bend in it. For this next one, rational functions, there's a whole bunch of these that look very different from each other. The one we're looking at is this one that has the two branches, but definitely understand that we can have the branches on the same side, and we can have like 3 or 4 different. They get pretty crazy. The parent equation we're dealing with for this one is just 1 over x, and we can modify that by adding things in the denominator or outside the denominator. We don't actually have to have just x's down here. There can also be x's in the numerator for these, but it'll give you a much different shape than this. But the hallmark of all these is that you have some kind of variable in the denominator. Because we have variables in the denominator, it is possible if you plug in the wrong stuff to make the denominator 0. And that would be very unfortunate because we don't like to divide by 0. So the domain on these in general, the denominator cannot equal 0. Everything else is okay, but we can't do that. Now the range is going to vary widely. In this particular one, we have something called a horizontal asymptote, where we're getting closer, but somehow not really able to touch the y value 0. And we can have asymptotes at any y value. We can have vertical asymptotes too, as you see here. We'll talk about all of that later. The key here is to realize that with rational functions, some things usually get left out of the domain and the range. The absolute value function is pretty wild. It's this V shape. It's kind of like a parabola, but it's got a sharp corner instead of a curve. So V shape, V for victory there, or value. The parent function, we have these little vertical bars that you've probably seen before. We can put things inside, we can put things out in front, lots of ways to modify these. The domain on this one, we can take any x value we want. However, the range, just like the parabolas, is limited. You can only get the positive numbers or 0 out of this. The next function we'll look at is the radical function, or the square root function. There's other kinds of radicals, but we're just looking at square roots. Here's the square root graph. So this one kind of looks like an R, but it has an endpoint, and that's the first function we've seen so far that has an endpoint at one end. The parent equation for this is, of course, the square root of x, and we can put things inside, we can put things outside. Domain on this. There's some x values that we cannot plug in. Everything over here can't get plugged in because you would be taking the square root of a negative number, which you've probably heard is a bad idea. In terms of the range, we also can't get anything below 0 because, how is a square root going to spit out a negative number if you can't even plug one into it? So our domain is everything greater than or equal to 0 for the x's, and the range is the same for the y's. For the exponential functions, we've got this shape here, which kind of looks like a parabola going one direction but not the other. It's actually more of like a curved L if you need to use a letter, either backwards or they could be going forwards as well. And there is no one parent function for this. It's more of a parent form where you have some number times another number that's being raised to a variable. That's where really what you get for an exponential function is this variables in the exponent. We can do things to the stuff inside the exponent. We can have a number out in front. This e here is actually a number that you may or may not have encountered at this point in high school. The domain for this is all the real numbers. Exponents can be positive, negative, 0, doesn't matter. For the range, though, you'll notice that we can't quite get to 0 or negative. Because if you think about this, exponents, you're just taking a number and multiplying it by itself over and over again. If you start with a positive, you can't get 0 or negative by multiplying it. So the range is just going to be all the y values greater than 0 because of this horizontal asymptote on the x-axis. Closely related to the exponential function family is the logarithmic family. This looks kind of like an R, except it doesn't have endpoints, unlike the square root function. So parent function for this, just like the exponentials, it's more of a parent form. So we have log, there might be a base. If you don't see a base down here, it's invisible base 10. ln of x is really a log function with base e. If you have no idea what this is because you've never seen it, that's okay. We'll go over it later. But if you're taking calculus or something, hopefully you've seen logs by now. So for examples, we can have different bases, different things inside. And here's some fun with the ln function, which again is just a log with base e. The domain on this. We can't get zeros plugged in. We can't plug in negatives for these. And then for the range, you can actually get all the real numbers back. So if you think about this being the inverse of the exponential functions, notice that for the exponential functions, you could plug in anything you want, but you couldn't get anything back. Here, there's limits on what you plug in, but you can get anything back. So notice how the domain and range swap between this and the exponentials. So there are many more function families that we haven't looked at. We're going to stop here with sinusoidal, though. Enough's enough, right? So this one is one of these wavy ones. And the parent functions, you actually can get this kind of shape from a sine function or a cosine function. And if you haven't gone over what those are, we'll go over it later. So examples, we can have stuff inside the sine function or the cosine function or outside. For the domain, these functions go forever in both directions. You can plug anything you want into them. The range, however, for sine and cosine, just the regular functions, without any bells and whistles, that is going to be limited between -1 and +1. It just keeps oscillating between those. So now that we've got all those function families under our belts, we're going to talk about one way to classify them that often comes up, and this is asking whether a function is even, odd, or neither. So what do these things mean? An even function is a function that has y-axis symmetry. An odd function, in contrast, is a function that has origin symmetry, which is a rotational kind of symmetry, like if you rotate something about the origin. To test for evenness, basically what you have to do, since you're talking about y-axis symmetry, you have to plug in -x wherever you see +x and see if it comes out the same. If it does, the function's even. So here, we're basically asking if I plug -x in for this x and this x, like so, will that, if I simplify it, give me back the original function? So we just have to apply our exponent rules. We have a negative to the 5th power. That's still going to be negative. So this will be -4x to the 5th, and this will be -6x. And as you might imagine, that is not the same as 4x to the 5th plus 6x. So we can say that this is not even. Next, we're going to perform the odd test. For this one, we're still going to plug in -x for x, but now we want to see if it negates the whole expression. If it does, then the function would be odd. So we're going to start very much the same, plugging in -x here, but instead of just leaving the original the same, we're actually going to stick a negative out in front of all of it. And now we're going to see if these two expressions come out the same. If you've already done the even test, you know what the left side is going to come out to. It's still -4x to the 5th minus 6x. But here, we have to distribute this negative on the right side. That'll give us -4x to the 5th minus 6x. Since these two expressions are exactly the same, we can conclude, without even looking at a graph of this thing, which is good because I don't know what the graph looks like, we know that this has odd symmetry, or odd. It's an odd function. Now, if you had done both these tests and neither test worked, we would conclude the function was neither even nor odd. Most functions aren't either of these things, right? I mean, how many functions have origin symmetry or y-axis symmetry? But it's nice when you find one that does. So, to see if you've got the hang of it, try out the even and odd tests on these two functions. Pause the video. We'll bring it back together in a minute. All right, let's see how you made out. So for this one, let's plug in -x. So we have -x quantity to the 4th minus 8 times -x. And we'll see if that gives us what we started with. This becomes +x to the 4th. This becomes now minus, so plus 8x plus 16. That's pretty close, but it's not exactly the same as what we started with. So we would conclude this is not even. Let's try the odd test now. Now we're going to negate this entire function and see if plugging in -x gives us that. So we still have x to the 4th plus 8x plus 16 on the left. On the right side, we have -x to the 4th plus 8x minus 16. Again, it's pretty similar, but not quite close enough. So this is not odd either. Since it's neither even nor odd, then we would just say neither for this one. For example 3, plugging in -x into the x squared there, we've got -x squared. So this x becomes positive when you square it, but then you still have this negative out in front. So this becomes -x squared minus 8. That's exactly what we have on the right side as well. So this one actually comes out even. So that's it for this lesson. We've seen a whole lot of different things. We learned how to use our calculators. We saw function families. We even learned about even-odd functions. Until next time, this is Mr. Sutton signing off.